So here we are at Chapter 6. When we get done with this chapter, we'll be halfway there. And in Chapter 6, we'll be talking about wide area networking concepts, architectures, and services. More specifically, this chapter focuses on WAN business principles, the principles that will be driving and determining the features of our WAN that we will need, and WAN specifications. Also, we'll look at WAN transmission technologies, which is physical layer, and we'll be covering T1 and SONET. We'll also talk about WAN switching technologies, which occurs at the data link layer. We'll look at circuit switched as well as packet switched. And then we'll cover WAN architectures, which will include X.25, frame relay, ATM, and MPLS. We'll also have a little bit at the end on where WANs are headed with WAN Evolution. This is a list of network design principles, and these principles would apply in a local area network as well as a wide area network. I think we're just maybe a little bit more sensitive sometimes to the wide area networking side of things, in the sense that from a financial sense, because we're having to pay an outside provider usually to make that point-to-point connectivity for us. Internally we have full control. When we're working on a LAN, we have full control of all of these different principles that we're taking a look at here. But when you go out and you want to buy a WAN service, then certainly you're going to have to really do your homework, and make sure that all of these principles are going to meet the needs of your company as far as the wide area service is concerned. So, performance certainly an issue. One of the biggest issues that we deal with links between sites. Cost reduction, always important in business. Security and auditing. We're going through networks again that we don't have any control over, and so there could be people listening in on the links between point A and point B, and so we certainly want to have security in place, and then auditing as well. Availability, reliability, we got to make sure that we can always have communication between two sites. Manageability and monitoring, the ability to increase bandwidth, say dynamically if need be. Also being able to monitor the traffic to see when we're reaching our bandwidth capacity, or are we utilizing even 50% of what we're paying for. Quality of service can be an issue, especially when we're doing like video conferencing and things of that nature. And support for business recovery planning. So when you're considering establishing a wide area network architecture, you got to consider what types of data you're going to be transmitting over that wide area network architecture. And so these are just some examples of things that might be from any particular company might be transmitted. So voice, probably. Data, most likely. Video, that's more common these days. Imaging, especially in medical fields. And then faxing documents might also be a possibility. And so when you look at the graphic, the little table then underneath of each of these individual images, you'll see these are things that we have to consider as IT managers. So what are the demands of our user? That's going to dictate pretty much the traffic that's going to flow over the WAN. But protocol specifications need to be supported here. For instance, if we're going to run video conferencing, then quality of service will more than likely be something that must be included. Our access line, what's going to be the bandwidth. Network services, what types of services will be supported by the WAN provider. Our network-to-network interface, that's going to dictate the types of equipment that we're going to have when we make the connection from our local area network to the wide area network service. Routing, we're going to be able to, or need to, be able to forward data from various locations to other locations within the organization. And so also our switching architecture and our transmission architecture is going to be important. Is it circuit switching, packet switching more than likely, and then the various transmission architecture methods that we have. So we'll talk about things like SONET technology and T1 technologies and stuff like that here in a little bit. This graphic represents WAN specifications. You can see that the OSI layers are listed there on the left and the WAN specs are listed on the right. Primarily, WANs are designed around the physical layer and the data link layer, although in X.25 there is a network layer component. If you focus in on the data link layer there under the WAN specifications, you can see the various protocols then that are used, like Link Access Protocol B and Frame Relay and HDLC and the point-to-point protocol and SDLC. We are going to go through and take a look at WAN transmission technologies now. So we'll be covering T1 and SONET. T1 is a copper-based technology and SONET is a fiber-based technology. So we'll start with T1. This is the standard for digital transmission circuits in North America, and it is a bandwidth. This is a synchronous bandwidth, meaning the up and down speed are the same, of 1.544 megabits per second. In Europe, they have a little bit of a different standard. They use a different framing scheme than does T1. And so the E1 standard will provide a bandwidth of 2.048 megabits per second. So think back now to the previous chapter when we were talking about pulse code modulation. We were talking about sampling 8,000 times a second. We were sampling an analog signal, and we're using 8 bits then to represent what the wave looked like, the analog sound wave looked like at 1/8,000th of a second in time. So again, I talked about the DSO being the basic channel of the North American anyway telecommunications system, and so this shows you now how we take 24 of those DSO channels and we combine them together to create the T1 transmission service, which gives us again 1.5 megabits per second, precisely 1.544 megabits per second. So you can see that each byte of a channel is placed into the T1 frame here. So the first grouping of bits that you see there, the pink bits, would be channel 1, 8 bits from channel 1, and then we have the next sequence there from channel 2. This is the next 8 bits, and then channel 3 is the next 8 bits. So all the way up through 24 channels. And then you have a bit that marks the start of the frame. That's the red bit that you see on the far left there. And so if you can remember that you've got this one extra bit, that's how you come up with the 1.544 megabits per second in the T1 when you multiply 24 times our DSO channel of 64 kilobits per second. So this takes you through the math. You've got 24 channels per frame and 8 bits per channel, so that's 192 bits per frame. Now we have to add that one framing bit, so that's 192 bits plus one framing bit, so that's actually 193 then total bits per frame. Now multiply that times our 8,000 frames per second, remember the sampling rate, and that's how you come up with the 1.544 megabits per second of the T1 transmission service. Then we need to gather up those frames that we were seeing in the previous slide, and they get organized into super frames and extended super frames. So when you look at this graphic here, what you're looking at is two separate super frames, and a super frame then is a collection of 12 frames. So again, you've got your 24 channels of 8 bits each, the 193 bits. 12 of those combined together make up a super frame, and then when you take the two super frames and put them together, then we have an extended super frame, or a total of 24 frames. This table represents then the WAN transmission services that are available in the United States. So we start with the DSO level. One voice channel, 64 kilobits per second, and then we take 24 of those, put it together, come up with the digital service level of DS1, which is referred to as T1 when we're talking about the actual Transmission service. So that's what you would actually be purchasing from the telecommunications company. We combine two DS1s together and we get a DS1C, which is 48 voice channels, also known as a T1C. The next level up is a DS2, also known as a T2, that's 6.3 megabits per second. DS3, also known as a T3, is 44.736 megabits per second. And a DS4 is also known as a T4 and is 274 megabits per second, 4,032 voice channels. T1 and T3 are the most common service levels that are usually utilized by corporations. It's also delivered using 4 copper wires, so there's 2 twisted pairs in the wiring that's used for a T1 service. T3 service most commonly delivered using optical fiber or fiber optic cabling. This table then is a listing for the E standards established by the International Telecommunications Union, or the ITU. So they also have digital service levels 1, 2, 3, 4, and 5, and the corresponding E's on the right hand side there are the transmission services of E1, E2, E3, E4, and E5. And then you can see the various transmission rates for each of those transmission services. Next, we take a look at some of the technology that's involved in being able to utilize a T1 transmission service. So the key component in T1 service is what's called a CSU-DSU, a channel service unit, data service unit. And so this is the device that actually interfaces between the carrier's termination of the T1 service at our customer premises. So when you have the jack that is installed, that is your T1 service, usually in your wiring closet, then you'll hook to the T1 jack up to the jack on the CSU-DSU, which usually is attached a jack that's part of a router. T1 is commonly delivered again as a 4-wire circuit, 2 pairs of wires, 1 pair for transmitting, 1 pair for receiving. And it is physically terminated with a male RJ48C connector. So in Ethernet we use RJ45. In a T1 environment it would be an RJ48C connector. Most of the T1 CSUs, DSUs provide the corresponding RJ48C female connector to interface with that male counterpart provided by the carrier. Of course, the T1 CSU DSU is going to transfer at 1.544 megabits per second, and usually it's connected to local devices over higher speed connections such as V.35s, RS530s, or RS449s, or most commonly Ethernet. A CSU DSU is often able to communicate status and alarm information to various network management systems using the Simple Network Management Protocol, or SNMP. We'll take a look at that protocol later on when we get to the management chapter. Now here's a sample example of how we might be connected to the various WAN service providers. You can see in the top of this graphic here the PBX system is connected to a channel bank that has the ability to connect to the T1 system. PBXs can be connected. If you remember when we were doing the PBX discussion in the previous chapter, we talked about the trunk lines coming in from the telecommunications systems, and so they can connect directly themselves to the T1. Then also you have a router here that has an inverse multiplexer connected to it. So this is allowing for multiple T1 lines to be connected to the customer side. And then at the very bottom there we have a router that's connected to just a simple old T1 CSU DSU, which then connects to the T1 link on the telecommunications side. And of course in the telecommunications cloud you can see all the various switches there that carry the traffic from one location to the next, and then between clouds they're using an OC3 link. Remember we talked about the T3 service, and OC is just optical carrier, so it's the same level of service as the T3, just simply using optical fiber optics as the connection then between the switches there. So the telecommunication system obviously is using much higher speed backbones to connect all of their various networks together. So the T services we just looked at, remember, are copper-based, and so now we're going to take a look at SONET and SDH, which are fiber-based. And so SONET is the synchronous optical network. It is an optical transmission service used in the U.S., makes use of time division multiplexing as its technique to deliver high bandwidth. The difference between a T1 and a SONET is higher transmission capacity of SONET due to its fiber optic media, and it does have a slightly different framing technique as well. It uses the ANSI T1.105 and T1.106 standards. SDH, or synchronous digital hierarchy, is the optical method that is used in the rest of the world. Now here you can see we've got a table then that lists the SONET SDH service levels. So STS1, 51.84 megabits per second, ST3, 155.52 megabits per second, all the way down there to the STS 3073, which is 159.25 gigabits per second. On the left too there you'll see the framing methods. For SONET, it uses the STS, Synchronous Transport Service, as its way of framing the bits. And then in SDH they use the Synchronous Transport Model, or STM. And this graphic then represents SONET's framing, the STS that we just talked about. You can see that it is comprised of 90 columns and 9 rows, and that makes up one STS frame. The first 3 columns of the STS frame are the transport overhead, so that's going to be the header information basically. And then the remaining 87 columns is known as the synchronous payload envelope. That's where the data will be. Also note that each column is equal to a byte, or in other words 8 bits. And so then you can see that we've got the math down here below. We've got 90 octets per row, 8 bits per octet, so that's 720 bits per row. And 720 bits times the 9 rows is giving us 6,480 bits then per frame. And again, if we sample that at 8,000 times per second, then we're going to get the base rate of 51,840,000 bits per second, so 51.84 megabits per second. This graphic just shows you that in the STS framing that overhead section is actually broken down into 2 subsections. The section overhead, which is made up of 3 rows, and the line overhead, which is made up of 6 rows. And then also there's a section there to the right you'll see that's referred to as the path overhead, which is all 9 rows and 8 bits wide, 1 octet wide, and that's actually embedded in the payload portion of the frame. SONET is transmitted on a topology known as the unidirectional path switched ring. So you can see that what's going on here is we have dual rings, each going in opposite directions. One ring carries the primary signal, and the second ring, the redundant ring, is carrying the protection signal. So the idea is that if either ring were to go down, we still have successful communications occurring. This is a little bit more sophisticated SONET topology known as BLSR, the bidirectional line switched ring. So you can see in this case now we actually have 2 pairs of rings going in opposite directions, and each fiber is going to have 6 STS1As as far as the data that's flowing through that particular channel. And so again, it's just a matter of having redundancy so that if a single line goes down or a single system goes down, that the communication process can still continue to work. One of the ways of increasing the capacity of a fiber optic network, a single fiber, is by using wavelength division multiplexing, or WDM. And so the idea here is that we can actually transmit more than a single wavelength on a single fiber. So we've got multiple wavelengths over a single fiber. And so if you remember back to elementary school, when you took light and you broke it in, used a prism to break it into different colors, and so each of those colors is a different wavelength, and so that's how we can simultaneously then have multiple signals being transmitted over a single mode fiber cable. Wavelengths are usually 50 and 100 gigahertz apart. So there's, if you remember the guard band, when we were looking at earlier technologies there, talking about voice transmission, how they have the guard band to separate the different, the voice channel from the data channel. And so basically the same thing going on here, just each individual data channel is being separated by 50 or 100 gigahertz. And then to increase the number of waves, channels that we can have on a single fiber is another technology called dense wavelength division multiplexing, or DWDM, and this can actually get us bandwidth up to 1 terabit per second on a single fiber. Of course, that's in theory. Individual wavelengths are called lambdas. Next, we take a look at switching methods, which we've covered a little bit of this before. Remember that switching allows for temporary connections to be established, maintained, and terminated between message source and message destination, and that there are two primary switching techniques that are employed: circuit switching and packet switching. First, we'll be taking a look at circuit switching, and circuit switching is then subdivided into two categories: leased-lines, which is a dedicated always-on connection, also known as point-to-point connections, and then also we'll take a look at dial-up, which would include telephone, ISDN, and DDR. After circuit switched, we'll take a look at packet switched, and in packet switching we're talking about technologies like X.25, frame relay, and also cell relay technologies, which would be ATM and MPLS. So here's a little more detail then about circuit switched WANs. In a circuit switched network, a switched dedicated circuit is created to connect two or more parties, and this eliminates the need for a source and a destination address. There are two types of circuit switched WANs: leased-lines, which are dedicated always-on types of connections, or dial-up, which would be like a phone call where we establish the connection on a need-be basis. So essentially there's two ways of providing wide area communications, or connectivity I should say. Dedicated point-to-point connections, as we see in this graphic here, where you have all of the systems on the left individually connected to a system on the right there. So each one is a separate point-to-point connection. And then in the next graphic we'll see a little more efficient way of doing this. Some more information about leased-lines here. Your carrier allocates pairs of wires and facility hardware to your line specifically, and then circuits are generally priced based on the bandwidth that you require, as well as the distance between the two connected points. Also, leased-lines or point-to-point links are generally more expensive than our shared services like frame relay. So here now we see a shared link between all of the systems, and so what we're doing basically is we're multiplexing everything on the left onto a single backbone line, and then demultiplexing it on the right there, and then redistributing to the destination. So that's a single shared WAN link, instead of, if you think about this from a company standpoint and a financial business standpoint, instead of having to buy multiple lines to create those individual point-to-point connections we saw on the last slide, now we just have to have one point-to-point link, and of course you'd have to have probably a greater bandwidth, but still a little bit more efficient way of doing things. This is an interesting graphic here, as it shows a link that's established between two LANs using a leased-line circuit, and what we've got going on is, just imagine a facility in one location, one city on the left, and then another part of the company in a completely different city there on the right hand side. And so we've got the ability to have multiple computers at one site be able to put their packets multiplexed into the T1 link or the T3 link that we're sending into the WAN cloud there. And then once it reaches its destination at the remote site, then it is demultiplexed, and then all the packets can be distributed to their appropriate destinations. So we're actually having multiple messages here that are being multiplexed between our source and destination sites. Now, unlike leased lines, in a dial-up connection, the data connections are initiated on a need-be basis and then terminated when the communication is complete. So again, a telephone communication, a voice communication would be a good example of that. Also, ISDN is an excellent example of a dial-up circuit switching process. In the case of an ISDN connection, you have two channels, and they can be used independently for voice and or data. But in both cases, when we want to make the connection to the remote site, then there is actually a dial-up or an establishment process that is occurring. And so as soon as the data has been transmitted or the voice conversation is ended, then we do go ahead and terminate that connection. Here's a good graphic then representing a dial-up connection. And again, the fact that when we dial up, either using voice or data communications, we're actually establishing a dedicated circuit at that point in time. So all of the wiring and the facility hardware is reserved for that particular communication between point A and point B. The initiation is also referred to as a setup call from the source to the destination. And so again, because it's circuit switching, we are actually creating a dedicated circuit while the connection exists. As you should know by now, then, in a packet switch network, the packets of data are traveling one at a time from the message source to the message destination. And the packet of the data is going to go in one side of the public data network and come out the other, but it doesn't necessarily travel, each packet doesn't necessarily travel the same physical path each time. So in that particular case, one packet could arrive ahead of another packet, and so as the packet switches are passing the packets among themselves, the packets are being routed from the source to the destination, but not in any particular order. And also there's multiple destinations as well as multiple sources, and so that's why addressing information is very important in this type of switching. So here again, just a graphical representation, in this case of packet switching. So we've got the device on the left doing the transmission. It uses a packet assembler, disassembler, to take the message from the computer, hand it off to the packet switch data network, or public data network, the PDN. And again, it's going into this cloud where it can travel many different paths to get to its destination. And in this graphic, we're not seeing multiple sources and multiple destinations, but that's one of the advantages of having a packet switch network. We don't have just a point-to-point connection here. What we have really is a virtually switched network going on. Virtual circuits, I should say, being established between the sender and the recipient. And so since all these packets are taking different physical paths to get to their destination, again, it's real important that we have addressing information so we make sure that those packets get to the right destination. A couple of advantages of packet-switched WANs is that users are all sharing a common carrier resource. So the internet, for instance, is a good example of that. And so cost is generally much better than it would be with a leased or a dial-up point-to-point line. And in packet-switched WANs, virtual circuits are created that are using one of two methods, either connectionless or connection-oriented. Now, when we're sending data on a network, it's important to understand that there's two different ways of making the packet, I don't know, what the hell am I trying to say? Now, when we're sending data on a network, it's important to understand that there's two different ways of making the packet, I don't know, what the hell am I trying to say? Here's kind of the plus and the minuses of connection-oriented packet switch services. First of all, we do get reduced overhead because the LCNs, as opposed to having a full global address, is going to reduce the overhead. So we're reducing the amount of data link information that's being placed into each of the frames that are being transmitted. But there is increased overhead. That's the drawback then, the increased overhead, because we have to establish the connection, and then also we have additional point-to-point error detection and flow control information that's being added in the communication process as well. So really it's going to be whatever your business application is that's going to determine what's going to be the best choice, either connectionless or connection-oriented packet switch services. Now, when we're using connection-oriented packet switch connections between two sites, that's referred to as a virtual circuit, and there are two types of virtual circuits. One is a switched virtual circuit, or SVC, and the other is a permanent virtual circuit, or PVC. In a switched virtual circuit, there's a bit of a delay in the beginning while the actual circuit is being established. It's actually identifying the pathway that all of the packets are going to travel. And then the connection is terminated when the completed message has been sent. A clear request packet then is going to cause all of the SVC table entries that were originally set up in the establishment portion of that to be erased from the tables of all the switches. Then in a PVC, we still have the entries going into the tables on the switches when we establish the circuit initially, but then once the message is completed, the information is not erased at the completion process. So the PVC then is the equivalent of a virtual circuit switched leased line, but much less expensive. Another cell-based switching method that's used in wide area networks is the multi-protocol label switching method, or MPLS, and it uses what are called labeled switched paths, or LSPs, and so it's basically the equivalent of an ATM switched virtual circuit. So MPLS is a three-layer architecture, and we're looking at the outer layer here, which is the edge layer. And so this is where we typically find all of the non-MPLS devices, things like Ethernet switches and IP routers and whatnot. And if you look closely at the graphic there, you'll see then all of the non-MPLS devices are then being connected to the next layer in there, which is the access layer. Then at the access layer, that's where the LERs, or the label edge routers, exist. And they're responsible for taking all of that data that's coming in from those non-MPLS devices out there in the edge layer and then encapsulating it into MPLS frames. Also, the label edge routers establish, maintain, and terminate the label switched paths that go through the network core for any of the non-MPLS devices. And the core layer, then, you can see is formed by a mesh of label switch routers, or LSRs, and so they're responsible for taking the traffic from one location, all of the non-MPLS traffic that's been encapsulated there at the access layer, to then route it from location 1, say, to location 2 or to location 3, from point A to point B. Dense wavelength division multiplexing being the first one on the list there. We talked about that one previously. It gives us the ability to have multiple channels over a single fiber and gets us speeds up to terabits per second over a single fiber. Optical cross connects are also a technology that will assist in the growth of WANs. The previous method that was used was that every time that we wanted to route traffic at a CO or at a inter-exchange carrier switching station, they had to convert the optical into electrical, perform the routing, and then take that electrical and convert it back to optical again. and so optical cross connects will prevent or not require that electrical component in the middle, which obviously means that we'll be able to apply fiber-based routing, or I should say optical-based routing, much quicker. And then also another technology is optical add-drop multiplexers, which allow us to, again, basically bypass the electrical components, and using technologies that like mirrors and things like that allow us to add and remove frames from the optical network.